Chapter 3, the Rust Programming Language, Common Programming Concepts. This chapter covers concepts that appear in almost every programming language and how they work in Rust. Many programming languages have much in common at their core. None of the concepts presented in this chapter are unique to Rust, but we'll discuss them in the context of Rust and explain the conventions around using these concepts. Specifically, you'll learn about variables, basic types, functions, comments, and control flow. These foundations will be in every Rust program. Learning them early will give you a strong core to start from. Keywords. The Rust language has a set of keywords that are reserved for its use by the language only. Much as in other languages, keep in mind that you cannot use these words as names of variables or functions. Most of the keywords have special meanings, and you'll be using them to do various tasks in your Rust programs. A few have no current functionality associated with them, but have been reserved for functionality that might be added to Rust in the future. You can find a list of keywords in the Appendix A. Variables and mutability. As mentioned in Chapter 2, by default, variables are immutable. This is one of the many nudges Rust gives you to write your code in a way that takes advantage of the safety and easy concurrency that Rust offers. However, you still have the option to make your variables mutable. Let's explore how and why Rust encourages you to favor immutability and why sometimes you might want to opt out. When a variable is immutable, once a value is bound to a name, you can't change that value. To illustrate this, let's generate a new project called variables in your projects directory using cargo new variables. Then in your new variables directory, open up src/main.rs and replace the code with the following code that won't compile just yet. So you can see the code here. Save and run the program using cargo run. You should receive an error message shown in the output. Here's the output. This example shows how the compiler helps you to find errors in your program. Even though compiler errors can be frustrating, they only mean your program isn't safely doing what you want it to do yet. They do not mean that you're not a good programmer. Experienced Rustians still get compiler errors. The error message indicates that the cause of the error is that you cannot assign twice the immutable variable x because you tried to assign the second value to an immutable x variable. It's important that we get compiler time errors when we attempt to change a value that we previously designed as immutable, because this situation can lead to bugs. If one part of our code operates on the assumption that the value will never change and another part of our code changes the value, it's possible that the first part of the code won't do what it was designed to do. The cause of this kind of bug can be difficult to track down after the fact, especially when the second piece of code changes the value only sometimes. In Rust, the compiler guarantees that when you state that a value won't change, it really won't change. That means that when you're reading and writing code, you don't have to keep track of how and where a value might change. Your code is thus easier to reason through. But mutability can be very useful. Variables are immutable only by default. As you did in Chapter 2, you can make them mutable by adding mut in front of the variable name. In addition to allowing this value to change, mute conveys intent to future readers of the code by indicating that other parts of the code will be changing the variable's value. For example, let's change src/main.rs to the following. Here's what they want you to change it with. When we run the program now, we get this. We are allowed to change the value that x binds to from 5 to 6 when the mute is used. In some cases, you'll want to make a variable mutable because it makes the code more convenient to write than if you had only immutable variables. There are multiple trade-offs to consider in addition to prevention of bugs. For example, in cases where you are using large data structures, muting an instance in place may be faster than copying and returning newly allocated instances. With smaller data structures, creating new instances and writing in more functional programming style may be easier to think through. So slower performance might be a worthwhile penalty for gaining that clarity. Difference between variables and constants. Being unable to change the value of a variable might have reminded you of another programming concept that most other languages have: constants. Like immutable variables, constants are values that are bound to a name and are not allowed to change. But there are few differences between constants and variables. First, you aren't allowed to use mute with constants. Constants are just immutable by default. They are always immutable. So to say that again, constants are just immutable by default. They aren't just immutable by default, they're always immutable. You declare constants using the const keyword instead of the let keyword, and the type of the value must be annotated. We're about to cover types and type annotations in the next section, data types. So don't worry about the details right now. Just know that you must always annotate the type. Constants can be declared in any scope, including the global scope, which makes them useful for values that many parts of the code need to know about. The last difference is that constants may be set only to constant expression, not the result of a function call or any other value that could be computed at runtime. That could only be computed at runtime. Here's an example of a constant declaration where the constant's name is max_points and its value is set to 100,000. Rust's naming convention for constants is to use all uppercase with underscores between words, and the underscore can be inserted in numeric literals to improve readability. An example here. Constants are valid for the entire time a program runs within the scope they're declared in, making them a useful choice in your application domain that multiple parts of the program might need to know about, such as the maximum number of points any player of a game is allowed to earn or the speed of light. Naming hard-coded values used throughout your program as constants is useful in conveying the meaning of the value to future maintainers of the code. It also helps to have only one place in your code you would need to change if the hard-coded value needed to be updated in the future. Shadowing. Let's see, as you saw in the guessing game tutorial in the comparing the guess to the secret number section in chapter 2, you can declare a new variable variable with the same name as the previous variable, and the new variable shadows the previous variable. Rusticians say that the first variable is shadowed by the second, which means that the second variable's value is what appears when the variable is used. We can shadow the variable by using the same variable's name and repeating the use of the let keyword as follows. This program first binds x to a value of 5, and then it shadows x by repeating let x equal, taking the original value and adding 1, so that the value of x is then 6. The third let statement also shadows x, multiplying the previous value by 2 to give x a final value of 12. When we run this program, it will output the following. Shadowing is different from marking a variable as muted because we'll get a compile error if we accidentally try to reassign to this variable without using the let keyword. By using the let, we can perform a few transformations on the value, but have the variable be immutable after those transformations have been completed. The other difference between mute and shadowing is that because we are effectively creating a new variable, when we use the let keyword again, we can change the type of the value but reuse the same name. For example, say our program asks a user to show how many spaces they want between some text by inputting space characters, but we really want to store that input as a number. Here's an example below. This construct is allowed because the first spaces variable is a string type and the second spaces variable, which is a brand new variable that happens to have the same name as the first one, is a number type. Shadowing thus spares us from having to come up with different names such as spaces underscore stir and spaces underscore num. Instead, we can reuse the simpler spaces name. However, if we try to use mute for this, as shown here, we get a compiler time error. The error says we're not allowed to mute a variable's type. Now that we've explored how variables work, let's look at more data types. Let's look at more data types they can have. Data types. Every value in Rust is of a certain data type, which tells Rust what kind of data is being specified so it knows to work with that data. We'll look at two data type subsets, scalar and compound. Keep in mind that Rust is a statically typed language, which means that it must know the types of all variables at compile time. The compiler can usually infer what type we want to use based on the value and how we use it. In cases when many types are possible, such as when we converted a string to a numeric type using parse in the comparing the guess to the secret number section in chapter 2, we must add a type and annotation like this. If we don't add the type intonation here, Rust will display the following error, which means that the compiler needs more information from us to know which type we want to use. We'll see different annotations for other data types. Scalar types. A scalar type represents a single value. Rust has four primary scalar types: integers, floating points, numbers and booleans, and characters. You may recognize these from other programming languages. Let's jump into how they work in Rust. Integer types. An integer is a number without a fractional component. We used one integer type in chapter 2, the U32 type. This type declaration indicates that the value it's associated with should be an unsigned integer. Signed integer types start with an I instead of a U. That takes up 32 bits of space. Table 3-1 shows the built-in integer types in Rust. Each variable in the signed and unsigned columns, for example, I16, can be used to declare the type of integer value. Table 3-1, integer types in Rust. Each variant can be either signed or unsigned and has an explicit size. Signed and unsigned refer to whether it's possible for the number to be negative or positive. In other words, whether the number needs to have a sign with it, signed, or whether it will only ever be positive and can therefore be represented without a sign, unsigned. It's like writing numbers on a paper. Let's see, when sign matters, a number is shown with a plus sign or a minus sign. However, when it's safe to assume that the number is positive, it's shown with no sign. Signed numbers are stored using two complement representation. Each signed variant can store numbers from, I'm guessing that's a negative, 2n negative 1 to 2n negative 1 negative 1 inclusive, where n is the number of bits the variant uses. So an I8 can store numbers from negative 27 to 27 negative 1, which equals negative 128 to 127. Unassigned variants can store numbers from 0 to 2n, negative 1. So a U8 can store numbers from 0 to 28, negative 1, which equals 0 to 255. Additionally, the I size and U size types depend upon the kind of computer your program is running on. 64 bits if you're on a 64-bit architecture, and 32 bits if you're on a 32-bit architecture. You can write integer literals in any of the forms shown in Table 3-2. Note that all number literals except the bytes literal allow a type suffix, such as 57U8 and underscore, as a visual separator such as 1000. Integer literals in Rust. So, how do you know which type of integer to use? If you're unsure, Rust defaults are generally a good choice, and integer types default to I32. This type is generally the fastest even on 64-bit systems. The primary situation in which you'd use iSize or usize when indexing some sort of collection is when you're indexing some sort of collection. Integer overflow. Let's say you have a variable of type U8 that can hold values between 0 and 255. If you try to change the value to a value outside the range, such as 256, integer overflow will occur. Rust has some interesting rules involving this behavior. When you're compiling in debug mode, Rust includes checks for integer overflow that cause your program to panic at runtime. If this behavior occurs, Rust uses the term panicking when a program exits with an error. We'll discuss panics in more depth in the Uncoverable Errors with Panic section in Chapter 9. When you're compiling in release mode with the -- release flag, Rust does not include checks for integer overflow that cause panics. Instead, if overflow occurs, Rust performs two complement wrapping. In short, values greater than the maximum type the type can hold wrap around to the minimum of the values the type can hold. In the case of U8, 256 becomes 0, 257 becomes 1, and so on. The program won't panic, but the variable will have a value that probably isn't what you're expecting it to have. Relying on an integer overflow wrapping behavior is considered an error. If you want to wrap explicitly, you can use the standard library type wrapping. Floating point types. Rust also has two primitive types for floating point numbers, which are numbers with decimal points. Rust floating point types are F32 and F64, which are the 32-bit and 64 bits in size respectively. The default type is the F64 because on modern CPUs it's roughly the same speed as the F32, but is capable of more precision. Here's an example that shows floating point numbers in action. Floating point numbers are represented according to the IEEE-754 standard. The F32 type is a single precision float and a 64 has double precision. Numeric operations. Rust supports the basic mathematical operations you expect for all number types: addition, subtraction, multiplication, division, and remainder. The following code shows how you'd use each one in a let statement. Examples here. Each expression in these statements uses a mathematical operator and evaluates a single value which is then bound to a variable. Appendix B contains a list of all operators that Rust provides. The Boolean type. In most other languages, programming languages, a Boolean type in Rust has two possible values, true and false. Booleans are 1 byte in size. The Boolean type in Rust is specified using bool, B-O-O-L. For example, in the main way to use a Boolean value is through conditionals such as an if expression. We'll cover how if expressions work in Rust in the control flow section. The character type. So far we've worked only with numbers, but Rust supports letters too. Rust character type is language's most primitive alphabet type. And the following code shows one way to use it. Note that the character literals are specific with single quotes as opposed to string literals which use double quotes. I think they're referring to these puppies. Rust character type is a 4 bytes in size and represents a Unicode scalar value, which means it represents a lot more than just ASCII. Accented letters, Chinese, Japanese, and Korean characters, emoji, and zero with spaces are all valid character values in Rust. Unicode scalar values range from U plus 000 to UD7FF and U plus E000 to U plus 10FFF inclusive. However, a character isn't really a concept in Unicode, so your human intuition for what a character is may not match up with what a character is in Rust. We'll discuss this topic in detail in Storing UTF-8 Unicode Text with Strings in Chapter 8. Compound types. Compound types can group multiple values into one type. Rust has two primitive compound types: tuples and arrays. Tuples. The tuple type. A tuple is a general way of grouping together a number of values with a variety of types into one compound type. Tuples have a fixed length. Once declared, they cannot grow or shrink in size. When we create we create a tuple by writing a comma separated list of values inside parentheses. Each position in the tuple is a type, and the type of the different values in the tuple don't have to be the same. We've added optional type annotations in this example. The variable tup, I guess that's going to be the little abbreviation of it, binds to the entire tuple. Because the tuple is considered a single compound element, to get the individual values out of a tuple, we can use pattern matching to deconstructure a tuple value like this. This program first creates a tuple and binds it to the variable tup, and then uses a pattern with let to take tup and turn it into three separate values, x, y, and z. This is called deconstructuring because it breaks the single tuple into three parts. Finally, the program prints the value of y, which is 6.4. In addition to deconstructuring through pattern matching, we can access a tuple element directly by using a period, followed by the index of the value we want to access. For example, this program creates a tuple x and then makes a new variable for each element by using their respective indices. As with most programming language, the first index in the tuple is 0. The array type. Another way to have a collection of multiple values is with an array. Unlike a tuple, every element of an array must have the same type. Arrays in Rust are different from arrays in other languages because arrays in Rust have a fixed length like tuples. In Rust, the values going into an array are written as common comma separated list inside square brackets. Arrays are useful when you want your data allocated on the stack rather than the heap. We will discuss the stack and the heap more in Chapter 4, or when you want to ensure you always have a fixed number of elements. An array isn't as flexible as a vector type, though a vector is a similar collection type provided by the standard library that is allowed to grow or shrink in size. If you're unsure whether to use an array or a vector, you should probably use a vector. Chapter 8 will discuss vectors in more detail. An example of when you might want to use an array rather than a vector is a program that needs to know the names of the months of the year. It's unlikely that such a program will need to add or remove months, so you can use an array because you know it will always contain 12 elements. You would write an array's type by using square brackets, and within the brackets include the type of each element, a semicolon, and then the number of elements in the array, like so. Here, I32 is the type of each element. After the semicolon, the number 5 indicates the array contains 5 elements. Writing an array's type this way looks similar to an alternative syntax for initializing an array, but you want to create an array that contains the same value for each element. You can specify an initial value followed by a semicolon, and then the length of the array in square brackets as shown here. The array named A will contain 5 elements that will all be set to the value of 3 initially. This is the same as writing let A equal 3, 3, 3, 3, 3, but in a more concise way, accessing array elements. An array is a single chunk of memory allocated on the stack. You can access elements of an array by indexing like this. In this example, the variable named first will get the value 1 because that is the value at index 0 in the array. The variable named second will get the value 2 from the index 1 in the array. Invalid array element access. What happens if you try to access an element of an array that is past the end of the array? Say you change the example to the following code, which will compile but exit with an error when it runs. Running this code using cargo run produces the following result. The compilation didn't produce any errors, but the program resulted in a runtime error and didn't exit successfully. When you attempt to access an element using indexing, Rust will check that the index you've specified is less than the array length. If the index is greater than or equal to the array length, Rust will panic. This is the first example of Rust's safety principles in action. In many low-level languages, this kind of check is not done, and when you provide an incorrect index, invalid memory can be accessed. Rust protects you against this kind of error by immediately exiting, instead of allowing the memory access and continuing. Chapter 9 discusses more of Rust's error handling. Functions. Functions are pervasive in Rust code. You've already seen one of the most important functions in the language, the main function, which is an entry point of many programs. You also have seen the fn keyword, which allows you to declare a new function, new functions. Rust code uses snake case as the conventional style for function and variable names. In snake case, all letters are lowercase and underscores separate words. Here's a program that contains an example function definition. Function definitions in Rust start with fn and have a set of parentheses after the function name. The curly brackets tell the compiler where the function body begins and ends. We can call any function we've defined by entering its name followed by a set of parentheses because another function is defined in the program. It can be called from inside the main function. Note that we define another function after the main function in the source code. We could have defined it before as well. Rust doesn't care where you define your functions, only that they're defined somewhere. Let's start a new binary project named Functions to explore functions further. Place another underscore function example in src main.rs and run it. You should see the following output. The lines execute in order in which they appear in the main function. First, the hello world message prints, and then another underscore function is called and its message is printed. Function parameters Functions can also be defined to have parameters, which are special variables that are part of a function's signature. When a function has parameters, you can provide it with concrete values for those parameters. Technically, the concrete values are called arguments, but in casual conversation, people tend to use the words parameter and argument interchangeably for either the variables in the function's definition or the concrete values passed in when you call a function. The following rewritten version of another underscore function shows what parameters look like in Rust. Try running this program. You should get the following output. The declaration of another underscore function has one parameter name, x. The type of x is specified as I32. When 5 is passed to another underscore function, the print line macro puts 5 where the pair of curly brackets were in the format string. In function signatures, you must declare the type for each parameter. This is a deliberate decision in Rust design, requiring type annotations in function definitions means the compiler almost never needs you to use them elsewhere in the code to figure out what you mean. When you want a function to have multiple parameters, separate the parameter declarations with commas like this. This example creates a function with two parameters, both of which are I32 types. The function then prints the values in both of the parameters. Note that the function parameters don't need all of the same input. They just happen to be in this example. Let's try running this code. Replace the program currently in your functions project src/main.rs file with the preceding example and run it using cargo run. Because we called the function with 5 as the value for x and 6 is passed as the value for y, the two strings are printed with these values. Function bodies contain statements and expressions. Function bodies are made up of a series of statements, optionally ending in an expression. So far, we've only covered functions without an ending expression, but you have seen an expression as part of a statement. Because Rust is an expression-based language, this is an important distinction to understand. Other languages don't have the same distinctions. So let's look at what statements and expressions are and how their differences affect the bodies of functions. We've actually already used statements and expressions. Statements are instructions that perform some action and do not return a value. Expressions evaluate to a resulting value. Let's look at some examples. Creating a variable and assigning a value to it with the let keyword is a statement. In listing 3-1, let y equals 6 is a statement. Listing 3-1, a main function declaration containing one statement. Function definitions are also statements. The entire preceding example is a statement in itself. Statements do not return values. Therefore, you can't assign a let statement to another variable, as the following code tries to do. You'll get an error. When you run this program, the error you'll get looks like this. The let y equals 6 statement does not return a value, so there isn't anything for x to bind to. This is different from what happens in other languages such as C and Ruby, where the assign returns the value of the assignment. In those languages, you can write x equals y equals 6 and have both x and y have their value 6. That's not the case in Rust. Expressions evaluate to something and make up most of the rest of the code that you'll write in Rust. Consider a simple math operation such as 5 plus 6, which is an expression that evaluates to a value of 11. Expressions can be part of statements. In listing 3-1, the 6 in the statement let y equals 6 is an expression that evaluates to the value 6. Calling a function is an expression. Calling a macro is an expression. The block that we use to create new scopes, curly brackets, is an expression, for example. This expression is a block that in this case evaluates to 4. That value gets bound to y as part of the let statement. Note that the x plus 1 line without the semicolon at the end, which is unlike most of the lines you've seen so far. Expressions do not include ending semicolons. If you added a semicolon to the end of the expression, you would turn it into a statement which will then return a value. Keep in mind as you explore function return values and expressions next. Let's keep this in mind as you explore function return values and expressions next. Functions with return values. Functions can return values to the code that calls them. We don't name return values, but we do declare their type after the arrow. In Rust, the return value of a function is synonymous with the value of the final expression in the block of the body of a function. You can return early from a function by using the return key and specifically specify a value, but most functions return the last expression implicitly. Here's an example of a function that returns a value. There are no function calls, macros, or even let statements in the 5 function. Just the number 5 by itself. That is perfectly valid. That's a perfectly valid function in Rust. Note that functions return type is specified too as I32. Try running this code. The output should look like this. The 5 in 5 is the function return value, which is the type return type is, which is why the return type is I32. Let's examine this in more detail. There are 2 important bits. First, the line let x equal 5 shows that we're using the return value of a function to initialize a variable. Because the function 5 returns a 5, that line is the same as the following. Second, the 5 function has no parameters and defines the type of the return value, but the body of the function is the lonely 5 with no semicolon because it's an expression whose value we want to return. Let's look at another example. Running this code will print the value of x as 6, but if we place a semicolon at the end of the line containing x plus 1, changing it from an expression to a statement will get an error. Compiling this code produces an error as follows. The main error The main error message, mismatched types, reveals the core issue with the code. The definition of the function +_1 says that it will return an I32, but statements don't evaluate to a value which is expressed by an empty tuple. Therefore, nothing is returned, which contradicts the function definition and results in an error. In this output, Rust provides a message to possibly help rectify the issue. It suggests removing the semicolon, which would fix the error. Comments. All programmers strive to make their code easy to understand, but sometimes extra explanation is warranted. In these cases, programmers leave notes or comments in their source code that the compiler will ignore, but people reading the source code may find useful. Here's a simple comment. In Rust, comments must start with 2 slashes and continue until the end of the line. For comments that extend beyond a single line, you need to include 2 forward slashes on each line like this. Comments can also be placed at the end of lines containing code. But you'll more often see them used in this format with the comment on separate lines, on a separate line above the code. It's annotating. Rust also has another kind of comment, documentation comments, which we'll discuss in publishing a crate to crates IO section of chapter 14. Control flow. Deciding whether or not to run some code depending on if the condition is true, and deciding to run some code repeatedly while the condition is true are basic building blocks in most programming languages. The most common constructs that let you control the flow of execution of Rust code are ifs, expressions, and loops. If expressions. An if expression allows you to branch your code depending upon conditions. You provide a condition and then state. If the condition is met, then run this block of code. If the condition is not met, do not run this block of code. Create a new project called branches in your project directory to explore the if expression. In the src/main.rs file, input the following. All if expressions start with the keyword if, which is followed by a condition. In this case, the condition checks whether or not a variable number has a value less than 5. The block of code we want to execute if the condition is true is placed immediately after the condition inside curly brackets. Blocks of code associated with the conditions in if expressions are sometimes called arms, just like the arms in match expressions that we discussed in the comparing the guess to the secret number section of chapter 2. Optionally, we can also include the else expression, which we chose not to do here, to give the program an alternative block of code to execute should the condition evaluate to false. If you don't provide an else expression and the condition is false, the program will just skip. And if the block and skip the if block and move on to the next bit of code. Try running this code. You should see the following output. Let's try changing the value of number to a value that makes the condition false to see what happens. Run the program again and look at the output. It's also worth noting that the condition in this code must be a bool. If the condition isn't a bool, we'll get an error. For example, try running the following code. The if condition evaluates to a value of 3. This time the Rust throws an error. The error indicates that Rust expected a bool, but got an integer. Unlike languages such as Ruby and JavaScript, Rust will not automatically try to convert non-Boolean types to Boolean. You must be explicit and always provide if with the Boolean as its condition. If we want the if code block to run only when the number is not equal to 0, for example, we can change the if expression to the following. Running this code will print number was something other than 0. Handling multiple conditions with else if. If you can have multiple conditions by combining if and else in an else if expression, for example. This program has 4 possible paths it can take. After running it, you should see the following output. When this program executes, it checks if expression in turn and executes the first body for which the condition holds true. Note that even though 6 is divisible by 2, we do not see the output number is divisible by 2, nor do we see the number is not divisible by 4, 3, or 2 text from the else block. That's because Rust only executes the block for the first true condition, and once it finds one, it doesn't even check the rest. Using too many else if expressions can clutter your code, so if you have more than one, you might want to refactor your code. Chapter 6 describes a powerful Rust branching construct called match for these cases. Using if in a let statement. Because if is an expression, we can use it on the right side of a let statement, as in listing 3-2. Listing 3-2, assigning the result of an expression to variable. The number variable will be bound to a value based on the outcome of the if expression. Run this code to see what happens. Remember that blocks of code evaluate to the last expression in them, and numbers by themselves are also expressions. In this case, the value of the whole if expression depends on which block of code executes. This means the values that have the potential to be results from each arm of the if must be in the same type. In listing 3-2, the results of both the if arm and the else arm were i32 integers. If the types are mismatched, as in the following example, we get an error. When we try to compile this code, we get an error if the if and else arms have value types that are incompatible, and Rust indicates exactly where to find in the program. The expression in the if block evaluates to an integer, and the expression in the else block evaluates to a string. This won't work because variables must have a single type. Rust needs to know at compile time what type the number variable is. Definitely so it can verify a compile time that is type that is valid everywhere we use number. Rust wouldn't be able to do that if the type was number was only determined at runtime. The compiler would be more complex, and it would make fewer guarantees about the code if it had to keep track of multiple hypothetical types for any variable. Repetition with loops. It's often useful to execute a block of code more than once. For this task, Rust provides several loops. A loop runs through the code inside the loop body to the end and then starts immediately back at the beginning. To experiment with loops, let's make a new project called Loops. Rust has three kinds of loops: loop, while, and for. Let's try each one. Repeating code with loop. The loop keyword tells Rust to evaluate a block of code over and over forever or until you explicitly tell it to stop. As an example, change the src/main.rs file in your loops directory to look like this. When we run this program, we'll see again printed over and over continuously until we stop the program manually. Most terminals support a keyboard shortcut Control-C to interrupt a program that is stuck in a continuous loop. Give it a try. The symbol Control-C represents where you pressed Control-C. You may or may not see the word again printed after the Control-C, depending on where the code was in the loop when it received the interrupt signal. Fortunately, Rust provides another more reliable way to break out of a loop. You can place a break keyword within loop to tell the program when to stop executing the loop. Recall that we did this in the guessing game in the quitting after a correct guess section of Chapter 2 to exit the program when the user won the game by pressing the correct number. Returning values from loops. One of the uses of a loop is to re-entry an operation you might fail, such as checking whether a thread has completed its job. However, you might need to pass the result of an operation to the result of your code. To do this, you can add the value you want returned after the break expression. You use it to stop the loop. That value will be returned out of the loop so you can use it as shown here. Before the loop, we declared a variable named counter to initialize it to 0. Then we declared a variable named result to hold the value returned from the loop. On every iteration of the loop, we add 1 to the counter variable and then check whether the counter is equal to 10. When it is, we use the break keyword with the value counter times 2. After the loop, we use a semicolon to end the statement that assigns the value to result. Finally, we print the value in result, which in this case is 20. Conditional loops with while. It's often useful for a program to evaluate a condition within loops. While the condition is true, the loop runs. When the condition ceases to be true, the program calls break, stopping the loop. This loop could be implemented using a combination of loop, if, else, and break. You could try that now in a program if you like. However, this pattern is so common that Rust has a built-in language construct for it. While a while loop, listing 3-3, uses while, the program loops 3 times, counting down each time, and then after the loop it prints another message and exits. Listing 3-3 while using a while loop to run code while a condition holds true. This construct eliminates a lot of nesting that would be necessary if you used loop, else, if, else, and break, and it's cleaner. While a condition holds true, the code runs, otherwise it exits the loop. looping through a collection with for. You could use the while construct to loop over the elements of a collection, such as an array. For example, let's look at the listing 3-4. Listing 3-4 looping through each element of a collection using a while loop. Here, the code counts up through the elements in the array. It starts at index 0 and then loops until it reaches the final index in the array. That is, when the index less than 5 is no longer true. Running this code will print every element in the array. All 5 array values appear in the terminal as expected. Even though index will reach the value of 5 at some point, the loop stops executing before trying to fetch a 6th value from the array. But this approach is error-prone. We could cause the program to panic if the index length is incorrect. It's also slow because the compiler adds runtime code to perform the conditional check on every element on every iteration through the loop. As a more concise alternative, you can use a for loop and execute some code for each item in a collection. A for loop looks like the code in listing 3-5. Listing 3-5 looping through element of collection using a for loop. When we run this code, we'll see the same output as in listing 3-4. More importantly, we've increased the safety of the code by eliminating the chance of bugs that might result from going beyond the end of the array or not going far enough and missing some items. For example, in the code in listing 3-4, if you remove an item from the A array but forget to update the condition to while index less than 4, the code would panic. Using the for loop, you wouldn't need to remember to change any other code if you changed the number of the values in the array. The safety and conciseness of for loops make them most commonly used loop construct in Rust, even in situations in which you want to run some code a certain number of times, as in countdown example that we used while loop in listing 3-3. Most Rusticians would use a for loop. The way to do that would be to use a range, which is a type provided by the standard library, generates all numbers in the sequence starting from one number and ending before another number. Here's what the countdown looks like using a for loop and another method we've not yet talked about, reverse, to reverse the language. This code is a bit nicer, isn't it? Summary. You made it. That was a sizable chapter. You learned about variables, scalar and compound data, types, functions, comments, if expressions, and loops. If you want to practice with these concepts discussed in this chapter, try building programs to do the following. Convert temperatures between Fahrenheit and Celsius. Generate the 9th Fibonacci number. I'm not sure how that's pronounced. And print the lyrics to the Christmas Carol 12 Days of Christmas, taking advantage of the repetition in the song. When you're ready to move on, we'll talk about a concept in Rust that doesn't commonly exist in other programming languages: ownership.